Hello, AP Calc. Today I'm going to do part 1 of chapter 5, section 2. And now that we know how to estimate the area under the curve, we're going to want to actually find the exact area under the curve. So this is actually seems much more useful because exact is always better. But again, just going back to Riemann sums and RAM, we use those mostly when we can't find the exact area under the curve. And how do we find the exact area under the curve? Well, if you can imagine, if we have an infinite number of rectangles, then, surprising, right? Infinity limits. If we have an infinite number of rectangles, then the more rectangles we have, the more number of rectangles we have, the smaller each base, the closer to the exact value that we'll get of the area under the curve when we're using the rectangular approximation method. Like every time you did the rectangles and you had that little bit above and a little bit below, or however you do it, as you can imagine, that amount of things above and below will get smaller and smaller. The more rectangles you have, the smaller each base of each rectangle is. So, for instance, in this example here, you can see how there's gaps here, there's overshoots here. But the sum of all of these rectangles gives the approximation. Well, we're gonna want to make as many rectangles as possible, which is an infinite number of rectangles, and make each of these rectangles smaller. But let's just go through how this looks mathematically. Finding the area under the curve, we do the change of x for the area of the base, f of c sub k for the height of the rectangle. So wherever that is, whether that's on the right, whether it's a midpoint, whether it's some other value inside that rectangle, that determines the height. So the area under the curve mathematically, and this is a way, when we were writing all of those change of x times c of 1/2, or f of 1/2, change in x times x of 1/4, or 2/4, whatever it was, I can't remember now. But we wrote those out. We had a plus in between of each of them. Well, there's a faster way to write that. It's the sum figure. So I don't know if you've seen this sum. This is sigma, and it's the sum of all the rectangles, or sum of all the values from k equals 1, where c1, to k equals n, cn. Okay, so this is saying the sum of all the product, or it's the sum of all of these things when k starts with 1, and then it's k is 2, then k is 3, all the way up to k n, which would be the last rectangle. Okay, so that's what this represents, the sum of a bunch of things. So each time you take one of these, you're going to put a plus between them. That's what that sigma means. Okay, n represents the total number of rectangles, and so the more rectangles we have, the larger n becomes, the more precise our approximation will be. So I don't know. Hopefully that makes sense. That's pretty complicated stuff. And if you're a little bit lost, don't worry. I'm just showing this stuff here because it's part of the back end of how this stuff works. But we're not going to be writing sigmas. But again, this is just saying adding up all the rectangles. However many there are, n being the number of rectangles, you're going to take the first one plus the second one plus the third one. Okay. And as you can see, you can kind of see here in these screenshots of the book that the more rectangles you have, the less area that's overshooting and less area that's undershooting. Well, if we want to find the exact area under the curve, we're going to want to have an infinite number of rectangles. Essentially make the rectangles as small as possible. And this will give us the exact area under the curve. So the limit, as n approaches infinity, of the sum of k equals 1 of n of the product of the base times the height of the rectangle will give us the exact area under the curve. So we're using the limit to say that there's going to be an infinite number of rectangles, and we're going to take the product of each of those infinite number of rectangles. Crazy stuff, but this is what you need to know. We don't want to write this every time. Mathematicians didn't want to write this every time, so they came up with a abbreviation, and it looks like this. It's called the integral. So this long S-like thing, it's not an S. Don't make it look like your S's. Make it a little bit longer. It should be lower than your normal letters and higher than your normal letters by a little bit. This is called the limit of the integrations. The integration. So this a and b will indicate where you start on the x-axis and where you end of the parts that you want to find the area of. Okay, and then this f of ck is our function. So that is this function here, right? That's going to be the second part of the integration, that function. And this change of x is actually going to convert into dx, and that tells us what we're taking the function, what we're taking the integral with respect to. Okay, so and we're abbreviating this mess here like this. Okay, we call this the integral. Congratulations, the third part of calculus: limits, derivatives. This is integration, integrals. Okay. So let's do an example. Example 2 from the book here. And to start, we're going to do integration, but we're just going to take the integral of geometric figures. So you're just doing the area under the curve using geometry, essentially. So let me clear this out from what we had in here before. And use the graph of the integrand. Integrand is the part of the integral that's the function. And areas to evaluate the integral. Negative 3 to 3 of the function square root of 9 minus x squared. So I'm going to go into y equals, and I'm going to do second square root 9 minus x squared. Okay, and I'm going to do a zoom 6. Now this is probably not going to be the best window. It's all contained in this window, but I think I want to zoom in a little. So let me go, not zoom in. Actually, let me just change the window. Negative 3. Here, right here is where we're starting the function. We're finding the integral from this point here. Oops, I did 2 accidentally. 3 to 3. So that actually tells us where our x and y, or sorry, the lower and upper boundary for our x, we might want it to be there. And then if you remember the graph, it didn't go below the x-axis, and it doesn't go as high as 10. I think it's going to go up to 3. Let's see. Is this a good graph? Okay. Now it looks a little more ovalish. Now if I'm using geometric figures, so it's all contained in here, but if I'm using geometric figures, I'm trying to think of this geometrically. Maybe I should keep the window, keep it symmetric on both sides, so maybe I should go down to negative 3, so you can see that this should look like a semicircle. Now it actually looks a little stretched this way because it is a wider screen than it is high. So a zoom square actually I think might fix that. Yeah, okay, now it looks more like a, yes. So zoom square, what that does is it takes a window that you have and it will add to the x-axis so that the y-axis will be, how do I say this? So that the y-axis and the x-axis give a realistic image, because if you go from negative 10 to 10, negative 10 to 10, because this is a wider screen than it is high, it's actually stretched in the horizontal. So zoom square fixes that. It's just a problem because we like our screens not to be complete squares, because it looks weird when a screen is just a square, like exactly a square. In fact, you probably can't find one very many places. Maybe a watch, maybe these iWatches or whatever do it. But hopefully, okay, so this is the window I did here. That looks pretty good here too. Hopefully you can see that this is a semicircle. That's the goal, to see what kind of geometric figure it is. In this lesson, you're not going to do a lot of this throughout. We're going to be doing more complicated stuff than this in the near future. But for this section and this homework that's associated with this section, we're just going to find the area using geometry. Area under a curve is pi r squared. The area of the area of a circle is pi r squared. The area of a half circle is half pi r squared. So the area of this integral will be 1/2 pi r will be 3. Okay, and 3 squared is 9. 9 pi over 2 is our answer. Easy enough. The only thing that this example doesn't show that's important, I'm guessing it's important for this homework, I'm not sure for exact, but it will definitely be important in the near future, is one thing about, and we haven't done this yet, any area under the curve of a curve that's under the x-axis. So we always take the area under the curve to mean the area between the curve and the x-axis. So it's if the curve goes below the x-axis, then it's the area that goes from it up to the x-axis. So this is the area we're looking for here if the curve goes under the x-axis. Well, if that ever happens, this area is considered a negative area. Any area under the curve, under the x-axis, is considered a negative area. So this would be a positive area, and this would be a negative area. And if it would ask you to find the area of a curve that does something like this, you'd want to take the A1 and subtract A2, or take A1 and add negative A2. I'm guessing that comes up in the homework because I don't know why else I would have put that there, other than that does become very important in the near future. So that's all I have for this video. Just a few problems. Thank you and good day.